In this video, I'm going to introduce you to something called Green's theorem. In particular, we're going to look at the circulation form of Green's theorem. What we're trying to do now is move into 3 dimensions with all of the concepts we started building in one-dimensional calculus. If you recall, there was a fundamental theorem for line integrals, which was a version or extension of the fundamental theorem of calculus. And that said that the integral from a to b of the derivative of f with respect to x dx was equal to f of b minus f of a. Basically, this just relates the integral of the derivative of f with respect to x on a closed interval from a to b to the function values of f on the boundary of the interval. And then we saw that the integral over a region C of del phi dotted with dr was equal to phi at b minus phi at a. This one related the integral of del phi on the smooth-oriented curve C to the function values of phi on the boundary of C, or the endpoints of the region C. But there's still more we can do. When we work with simple closed-oriented curves that lie in planar regions of R2 space that are both connected and simply connected and have continuous non-zero tangent vectors at all points, there's something called the Jordan curve theorem that tells me that these curves have a well-defined interior, and that when the curve is traversed in a counterclockwise direction as viewed from above, the interior will always be on the left. This results in a unique outward unit normal vector that points to the right. And since the net component of our vector field that lies in the direction tangent to our curve gives us a circulation, it also tells us that something inside our well-defined interior is driving that circulation. And you can think of this as a net rotation in the field. So now we get to Green's theorem. Green's theorem is just another extension of my fundamental theorem of calculus, which in this case is going to relate the double integral of derivatives of a function over a region in R2 to function values on the boundary of the region. There are 2 forms of Green's theorem that we will work with. The first is the circulation form. And in this form of Green's theorem, we relate the circulation on the boundary of C to this double integral over the region R of a quantity that measures rotation at each point in R. So if C is a simple closed smooth curve oriented counterclockwise that encloses a connected and simply connected region in the plane, we can assume that my vector field F is given by a vector with components f and g, where f and g have continuous first partial derivatives in the region R. Then this tells me that the closed integral over C of f dot dr is equal to the closed integral over C of f dx plus g dy, and this is equal to the double integral over R of the partial of g with respect to x minus the partial of f with respect to y dA. The closed integral over C of f dot dr is a circulation. The closed integral over C of f dx plus g dy is a circulation. The integrand in the double integral, the partial of g with respect to x minus the partial of f with respect to y, describes the rotation of the vector field within C that produces the circulation on the boundary of C. This partial of g with respect to x minus the partial of f with respect to y is called the two-dimensional curl of the vector field. If the horizontal component of my field decreases in the y direction, meaning f sub y is less than 0, and the vertical component increases in the x direction, meaning g sub x is greater than 0 at some point p, then my partial of g with respect to x minus the partial of f with respect to y is greater than 0. The curl in this case will be positive, and the field will have a counterclockwise rotation at p. The double integral in Green's theorem computes the net rotation of the field throughout the region R. And the theorem also tells me that this net rotation throughout R is equal to the circulation at the boundary of the region R. Now, I may encounter what we call conservative vector fields, and when we apply Green's theorem to a conservative vector field, we get another very important result. If my vector field F is given by vector components F and G, and it is conservative, this means that its components satisfy the condition that the partial of F with respect to Y has to be equal to the partial of G with respect to X. If R is a region of R2 on which these conditions for Green's theorem are satisfied, then the conservative field gives me the closed integral over C of f dot dr is equal to the double integral over R of the curl of my vector field dA, and that is equal to 0. It's equal to 0 because the curl itself is equal to 0. Vector fields of this type are called irrotational because it produces zero circulation on closed curves in the region. Irrotational vector fields on simply connected regions in R2 space are conservative. So let's work an example. If I'm given a vector field F that is described by the vector with components 0 and x squared plus y squared, and my region R is defined as the set of all points x, y, such that x squared plus y squared is less than or equal to 1, then I want to compute the two-dimensional curl of the vector field, evaluate both of the integrals in Green's theorem, and check for consistency between them, and then state whether or not the vector field is conservative. So the first thing I want to do is compute the curl of my vector field. This means I'm taking the partial of G with respect to X minus the partial of F with respect to Y. The partial of G with respect to X is the partial of the quantity x squared plus y squared with respect to X minus the partial of 0 with respect to Y. This gives me 2x. Parametrizing the components for my vector field gives me the components for the vector of 0 and cosine squared t plus sine squared t, where r of t is equal to a vector with components cosine t sine t, which makes r prime of t equal to a vector with components negative sine t cosine t dt. The closed integral over C of f dot dr is equal to the closed integral over C of the vector with components 0, 1, dotted with a vector with components negative sine t cosine t dt. This is equal to the closed integral over C of cosine t dt, which now becomes the ordinary integral from 0 to 2 pi of cosine t dt is equal to 0. The closed integral over C of f dot dr is equal to the double integral over R of 2x dA. This becomes the integral from 0 to 2 pi of the integral from 0 to 1 of 2 cosine theta r dr d theta, and this also is equal to 0. So the two integrals do give me consistent results. Even though my integrals were both equal to 0, my vector field is not conservative because my curl is not 0. So now you get to try it. Pause the video, and given the vector field that is equal to a vector with components negative 3y and 3x, and given R is the triangle with vertices at the points 0, 0, 1, 0, and 0, 2, compute the two-dimensional curl of the vector field, evaluate both integrals in Green's theorem, and check for consistency, and then state whether the vector field is conservative. When you are ready, restart the video to check your understanding. Again, I want to compute the curl first. The curl gives me the partial of 3x with respect to x minus the partial of negative 3y with respect to y, and this is equal to 6. There are three paths I have to look at. One from 0, 0 to 1, 0, another from 1, 0 to 0, 2, and a third from 0, 2 to 0, 0. My r sub 1 of t is given by the vector with components t0, r sub 2 of t is given by a vector with components 1 minus t and 2t, and r sub 3 of t is given by a vector with components 0 and 2 minus 2t. r1 prime of t is the vector with components 1, 0, r2 prime of t is the vector with components negative 1, 2, and r3 prime of t is a vector with components 0, negative 2. F sub 1 is equal to the vector with components 0, 3t. f sub 2 is equal to a vector with components negative 6t and 3 minus 3t. And f sub 3 is equal to a vector with components 6 minus 6t and 0. So that the closed integral over c of f dot dr is the sum of three ordinary integrals. The integral from 0 to 1 of the dot product of the vector with components 0 and 3t with the vector with components 1, 0 dt, plus the integral from 0 to 1 of the dot product of the vector with components negative 6t and 3 minus 3t dotted with a vector with components negative 1 and 2 dt, plus the integral from 0 to 1 of the vector with components 6 minus 6t and 0 dotted with the vector with components 0 and minus 2 dt. I simplify these dot products and I notice that my limits of integration and my variable of integration is the same in all three, so that I can combine them into a single integral, the integral from 0 to 1 of 12t dt. This becomes 6t squared evaluated from 0 to 1, and it gives me 6. The closed integral over c of f dot dr is equal to the double integral over r of 6dA. This is equal to the integral from 0 to 1 of the integral from 0 to negative 2x plus 2 of 6dy dx. This is equal to 6 times the integral from 0 to 1 of 2 minus 2x dx, which is equal to 6 times the quantity 2x minus x squared evaluated from 0 to 1. My result is 6. Both integrations give me the same value and they are consistent, but the vector field is still not conservative because my curl was 2x, which is not 0. Now I do want to mention a little bit more about the power of Green's theorem here. In addition to computing the circulation in a vector field, we can use Green's theorem to compute an area when the vector fields are given by vectors with components 0x or y0. In the first case, we get the partial of g with respect to x is 1 and the partial of f with respect to x is 0, so that Green's theorem gives me the closed integral over c of f dot dr is the closed integral over c of x dy, which is the double integral over r of dA, and it gives me the area of R. In the second case, my partial of g with respect to x is 0, my partial of f with respect to x is 1, and Green's theorem here gives me the closed integral over c of f dot dr is equal to the closed integral over c of y dx, which is equal to negative the double integral over r dA, which is the negative area of R. We can combine both of these into a single statement. Under the conditions of Green's theorem, the area of a region R enclosed by a curve can be found by computing the closed integral over c of f dot dr, which is equal to the closed integral over c of x dy, which is equal to 1/2 of the closed integral over c of x dy minus y dx. So now I want you to try this as well. Pause the video and use the line integral on the boundary to find the area of the region bounded by an ellipse with semi-major and semi-minor axes of length 6 and 4 respectively. When you are ready, restart the video to check your understanding. The first thing I want to do is parameterize my boundary. This gives me x is equal to 6 cosine t and y is equal to 4 sine t, where 0 is less than or equal to t, which is less than or equal to 2 pi. dx is equal to negative 6 sine t dt, and dy is equal to 4 cosine t dt. My closed integral over c of f dot dr becomes the closed integral over c of x dy, which is equal to 1/2 of the closed integral over c of x dy minus y dx. This gives me 1/2 times an ordinary line integral from 0 to 2 pi of the quantity 6 cosine t times 4 cosine t minus 4 sine t times negative 6 sine t dt. This is equal to 12 times the integral from 0 to 2 pi dt, which is equal to 12t evaluated from 0 to 2 pi, or 24 pi, and that's the area of my region. This is working with the circulation form of Green's theorem. Be sure and let me know if you have any questions.